It's no problem.
The college is now using Microsoft Meet. I'm not sure. Last time we used to use Zoom. Google Meet.
Last time my chemistry teacher used to have Zoom, but she had to skip like every 40 minutes.
Yeah,
Like this.
yeah.
But then now she used Meet, right? That there's no need to stop, so she can keep
Okay,
on
I'll
going.
keep that in mind. Try to explore that. Zoom, the one thing good about it is that if you want to have longer time, then you have to pay, no? But usually you want free one, they don't allow you that long, no? 40 minutes. But I think 40 minutes is good
No,
enough.
Google Meet, right? It will allow you to record also, just for
I know.
free and let
40
you go
minutes
on
is
for
good
long
enough
time.
because 40 minutes allow you 5 minutes break. Because to teach you 1 hour is a bit long lah. Right? If you've got 5 minutes break, at least you can go and stretch yourself. The blood can go and circulate your mind, and then you can more fruitful lah. Right? Rather than sit down for 1 hour.
Right.
Usually in education, we will say after 40 minutes, your attention span goes down lah. So that's the reason. But we cannot do it in a school system lah. Even though we know, educational psychology will tell us all these are good things, but we cannot do that because for a simple reason, we don't have the time. Right? The school is in such a thing. Even in college, we also don't have the time to do all that. So those students who excuse themselves and go to the toilet break, then will find it helpful, no? Okay, let us carry on with transformer. More or less what you have studied before. Right, just to refresh your memory. Okay, as I say, you don't need to know all these gadgets. You need to recognize it only if you are going to do electronic or electrical engineering in university. Then you need to know the real thing. What we study is mainly theory. Right? That's your transformer. These are your capacitor. This is also capacitor. This one is electrolytic. Not sure what the others are about. Okay, so transformer changes, or we call it transform, and alternating PD. Right? It must be a changing PD, not a constant PD. Constant PD will produce a constant current, no changing flux. Right? Alternating PD will cause a changing current, then we'll call a changing flux. That's why we study about mutual induction. Right? So alternating PD from one value to another greater one, right? We call that step up, or from a smaller value, step down, right? Either transform the voltage to a higher value, step up, or to a smaller value, step down, using the mutual induction principle. That's what we just studied. Okay, but as I say, if you change the voltage, you will reduce the current. Right? You study that. Okay, so there is your primary coil. There's your laminated soft iron core. You don't need to know too far about that. A level, you need to know what's the purpose of soft iron core, but STPM, you don't need already. I think they removed it from the syllabus. You just need you to remember what you have studied in your SPM. Secondary coil. Right? And then we go to symbol, iron core, got stroke there, air core, nothing there. Okay, so that is your primary coil, the red one. Blue one is your secondary coil. Okay, so that's a simple transformer to help you understand. You got a primary coil, and then your secondary coil, and both of them wound on the soft iron core. Right? There's a laminated iron core. Primary coil, secondary coil, no electrical contact. Right? They are not joined by wire. That's why we say no electrical connection between secondary and primary. But soft iron core provide a magnetic link. That soft iron core gather all the magnetic field or magnetic flux density, gather all the lines and pass it through the secondary coil. That's why it's called a magnetic link, not electrical link. That means there's no wire connecting the two wires. The core is continuous, right? This iron core is continuous. There's no break there because you want the magnetic field to go from the primary to the secondary. So the core is to prevent any loss of flux there. You gather without the core, the flux will be lost, right? Like here. Let me just right? Like in here, right? Those that are going out that way are lost, right? All those that are outside there are lost. But if you put a iron core there, it gather all these flux that have be lost together into the secondary. Right? So the core, that core there, iron core, gather all the magnetic field lines and pass it to the secondary. Okay, so there is an alternating voltage in the primary. There's a changing current in the primary. So it will produce a changing magnetic flux, right? The flux, there's a field passing through the secondary. Right? You can use your right hand, right? Right hand grip rule. The fingers represent your field, direction of the field, and the thumb represent the polarity. So there's a north pole there, there's a south pole there. So there's a magnetic field going through the secondary, coming down in the loop there. So the changing current causes a changing field causes a changing flux in the secondary, and then you produce a changing induced EMF in the secondary. Right? Yeah, right. Changing flux induce an alternating voltage in the secondary. So because there's a changing flux, there's a changing EMF in the secondary. So when the current reverse direction changes direction, EMF in the secondary reverses direction, also the same thing. It will change direction. Frequency of secondary voltage is the same as frequency of the primary voltage. Right? Because it's the primary that change, that cause the secondary to change. So the frequency in the primary and frequency secondary must be the same. So that current is in phase with the flux, but it is not in phase with the secondary because of Lenz's law. Right? It's not in phase with the secondary voltage. How does it work? Let's summarize for you. Current flowing in causes a magnetic field in the core. Right? This magnetic field is from the primary coil. Right? So that magnetic field track or pass through the secondary. Changing current produce a changing flux. Right? That's your magnetic flux in the secondary changing. Then we apply Faraday's law, tell us there's going to be an induced EMF in the secondary. Right? Lenz's law tell us the induced current or induced EMF flow to produce a field opposing the direct field. Right? Opposing this direct field. Right? So the primary current and secondary current are not in phase. In phase means they are changing. Primary current goes up, secondary current goes up also. But no, right? It's opposing it. And remember that the primary current changes direction, the secondary induced current also changes direction. Frequency of primary and secondary is the same. It doesn't change because it's the primary that changes that causes the secondary to change. Okay, so I just reviewed you the same thing. More mathematical. Right? That's how you calculate your change in flux. Okay, the flux at BAN. So alternating voltage applied to primary. Right? That's your current flowing. Right? And your B, right? Magnetic field that's coming out from a primary is proportional to the current in the primary. And then we can calculate that this as we have done the mutual induction principle. Use the solenoid formula, treat this as solenoid. Right? Produces a changing flux. Right? Second, the changing flux is a secondary. Right? Because the current is changing, the flux is also changing in secondary. Then we can calculate our changing flux. Right? That's your flux, maximum flux, sine omega t. Then we can apply changing flux, apply Faraday's law. There's a Faraday's law. Then we can see that there's an induced EMF is secondary. Right? So current reverse direction, secondary current also reverse direction. Right? Frequency is the same. Right? That's a change. Frequency of secondary voltage is the same as primary voltage, but 90 degrees out of phase. Right? Because of that negative sign there. Okay, so you just need to memorize this formula from your SPM. Voltage in secondary, voltage in primary. So if you use root mean square, this will be root mean square. So if you use peak value, this will be peak value. We study this in the next topic. So secondary voltage, primary voltage, number of turns in secondary, S is for secondary, P is for primary. Number of turns of primary. Okay, so you can either use for Vs and Vp if it's peak, then both use peak. If it's root mean square, use both root mean square. So if Ns is greater than Np, then it's a step up transformer. Np is greater than Ms, right? And then smaller, so the step down transformer. So usually we are interested in 100% efficiency, right? Power input because power output. And we just use this formula, right? This is a power input, it's a primary power, secondary power. Okay, so these two formulas are required. So we have completed all these formula you need to know for this topic. We'll do some question. Okay, summarize for you all the formulas that you need to know how to use. Okay, let's try some of this question from your reference book, page 220 to 227, number 6, 7, 8, 11, 19, 21. If you got time, we try the structure and essay. If not, you can do it as your homework, and we do it Wednesday, 3 to 4. Okay. Oh, for ideal transformer, no heat is lost. Right? No heat loss. Input energy is completely transformed into output energy. Remember that. So this formula you need to remember. Okay, this one you can go back and try yourself. We'll go over that. Let's try. This one. Try that. Try that. It's an old question. Review your SPM work. What is the answer? Diagram shows an iron core transformer. Assume 100% efficiency. Ratio of secondary turns to primary turn is 1 to 20. 240 volt. Right? Remember, this is root mean square value. 240 is root mean square value, not peak value. Always is root mean square value. It's connected to the primary coil. That's what it is. I'll show you. And the 6 ohm resistor is connected to the secondary. That's a 6 ohm secondary beside. What is the primary current? Yeah, what is the primary current?
C, the answer is C.
Okay, let's see. NP is here, NS is here. Right? IP can draw on the question paper, doesn't matter, to help you picture it. All the things like what is given here, NS over NP. Right? So from NS, VS, VP is NS, NP. Can calculate your VS. Right? VP is 240. That's your VP. Then use your.
Then V equals to IR, and then I equals to V over R.
The power supply here equals the power supply here. That's all. That's what we are using. Except they use resistance, so we got to use VS over R. Put in whatever is known. Right? 12 is here for secondary.
So we don't use V equals to IR.
V equals IR. No.
Yeah.
Power. We are using power. Power. Not V equals IR. Power.
Oh.
Power must equal to power, not power equals to voltage. Always remember that. We cannot use IS, IP because there's no, we cannot use IS, IS, because IS is not given. You can do that, you can calculate your IS if you want to. But it's straightforward to use your VS times your R because R is given. Okay?
Okay.
Okay. A protective device in the main circuit consists of a transformer with two primary coil A and B and a secondary coil as shown in figure 3.1. The primary coil each have the same number of turns. These two primary coil have the same number of turns and is wound on in opposite direction to the core. Opposite direction to the core. That's your secondary. The main supply is connected in series with the two primary coil and the electrical appliance. The secondary coil is connected to an electromagnetic switch. At one particular moment, the live lead is positive with respect to the neutral lead. On figure 3.1, mark arrow to indicate the direction of the magnetic field in the transformer core due to primary coil A alone. Label this arrow A. Due to primary coil B alone, label that B. Okay. So let's just go over that. Right, so that's your line. That's your neutral. You are told that at a particular moment, this is positive. So you are asked to draw the field. Where should the field be? Right, that's your current flowing. Right, it's going down. So use your right-hand grip rule. Right-hand grip rule. So that is your north pole. That's your south pole. Then draw a current. Draw your field. That's your current. So that's your field. Okay, that's your field. The current will go through. Come out here. Right, and then go down here. So apply your right-hand grip rule. Right, it's coming down here. Right. So if you use right-hand grip rule, okay, grip it. Then this will be your north. This will be your south. Right, so that's your A. Right, that's your B. Right, so same current. A and B have the same magnetic field strength or magnetic flux density. So they cancel each other out. Right, it doesn't matter if the current is changing.
So if they have the same thing, means they cancel it out.
They cancel out, you can see the two arrows are opposite to each other. They are the same strength. It's a vector quantity. So they cancel each other out. So there's no change in flux in the secondary, no EMF in the secondary. Can.
Can.
Okay. Yeah, what is happening? Hence, explain why there is no EMF induced in the secondary coil. So that's the reason the two field from coil A and coil B oppose each other. So no net field, no change in flux. So EMF equals to rate of change in flux, as your Faraday's law, does not induce EMF. Okay? Any comment? Anything not clear? Okay, if okay, we carry on. A fault, something happened, develops in the electrical appliance such that there is a current to earth. As a result, the current in the primary coil is no longer equals to that in the secondary coil. Right? Current in primary coil and current in secondary coil is no more the same. Right? Don't worry about the fault all there. What is the fault? You are told current in primary and current in secondary different. Still explain the effect of this fault on magnitude of the flux in the coil of transformer. Yep. So what happens if there's a difference in B? Yep. Yeah, using alternating current can the two magnetic field strength or magnetic flux density is different. So what's the magnitude? Today I explained the effect of this fault on the magnitude of the flux in the core of the transformer. Can or not? Previously, the two flux are equal and opposite, so they cancel each other out. Right? The magnetic field is a vector quantity, so it's in opposite direction. B in opposite direction, they cancel out. So now they are not equal. So there's a net magnetic field. There's a net magnetic flux. Okay. They're just applying Faraday's law. Right? Since the current is no longer equal, there exists a net changing magnetic flux across the secondary. Previously, no changing flux. Now, current are not equal. There's a difference in B. Right? So B is no more zero. So if B changes, there's a change in flux. Okay, explain. State and explain the effect of this fault on EMF induced in the secondary. So if there's a change in flux in the secondary, change in flux secondary, there must be an induced EMF. That's all. Change in flux across secondary resulted in EMF being induced in the secondary. That's your Faraday's law. Yep. Anything that is not clear? If clear, then let's go and do some more example. So you have all the checkpoint to do. Checkpoint 17.3, 17.4, 17.5 to do that. We'll try to do that on Wednesday. Okay, with no question, let us go to try our focus question. Okay, you can try that. The question that I given you earlier. 7, 8, 9 from your focus on STPM. Right? Try that while I gather the slide. Sometimes it take a little bit of time to 7, 8.
Teacher, I can download all the stuff like that's why I think
I didn't download anything.
Okay,
Maybe
okay. Check, go to your what do you call that? That one. The what do you call this file explorer? Check. Create another.
I'm trying to download your focus question.
Oh no. I mean just okay. No, press this PC, teacher.
Trying to do too many things.
No, check. File explorer. File explorer.
Okay, Eddie. Okay, Eddie.
No. I just want to know, Nietzsche, the file explorer.
We don't want to go and explore, explain, try all that. Afterward, got anything problem, we will be caught halfway.
No. This one I nothing want to. This one check. Never mind. After class finish, then I ask.
After class, we will do that. Now you are supposed to try the question. Right? You're supposed to try all these questions. 6, 7, 8, 11, 19, 21. We will go over that.
Teacher, do you think I can do it, Acha? I'm still afraid, Acha.
I told you already. Solution for you is after I teach you, you try the question. Review through.
Keep doing.
That is the most efficient way. Rather than a few days later, you forget what I teach you already. Then you have to learn all over again and try to recall.
Oh, that's worse.
So it's better, more efficient is I teach you already, spend 1 hour, review through, and go and do all the checkpoint question. That's to reinforce your formula. Make sure you know how to use the formula. And then
So keep trying, even though wrong, also keep trying.
Yeah, it doesn't matter. As long as you try it, you don't know it, you can look at the answer and you will learn something. If not, you can ask me the next week. That's the purpose of doing it. You learn yourself. I cannot learn for you. I cannot teach you. Right? Learning is your own self. You have to push it in yourself, just like maths. You cannot study maths one. Those who fail one, they try to study maths, cannot study one. You have to learn yourself. Teacher can teach you a certain amount, then you have to learn to apply the basic and then learn something yourself. Cannot teach you everything one. Okay, 6, 7, 8, let's try that. 6, 7, 8, 11. That's why now I'm forcing you to do in class because you don't do your homework. Now I'm forcing you to do in class. Then at least you force it in. If not, it's a waste. Okay, that's your number 6. An ideal transformer has NP turns.
Number 6 is C.
Right? NP primary and S secondary. Oh, we have only 10 minutes. When the input voltage is VP and output voltage is VS. Okay, so this is your STPM work. So you won't bother. A is correct, B is false, C is true, D is true. So you want the wrong answer, not correct, is B. Okay with that?
Oh.
Okay? If okay, let's go to number 7. This one? The graph?
Wait. Why is B false, not C?
Yeah? C is correct. C is upside down. Yeah, from here?
Oh, okay.
It's upside down. This one is direct. Okay, this is upside down. This is your SPM work. The one that is false is here. I've done for you already, the calculation there.
Okay.
Number 7. Yep. Diagram below shows the current. There's your current in the primary coil. of an ideal transformer varies with time. There's your time axis there. Which of the following graph correctly shows a variation of secondary voltage with time? You want voltage, so you are looking at induced EMF changing with time. Okay, this is mutual inductance, but it's also applying Faraday's law. That's all. So the current is changing in the primary, the induced EMF in the secondary. Yeah, voltage induced secondary. We are just using your formula E minus M di dt. So di dt is proportional to gradient of this one. So this is a straight line. This is also a straight line, negative direction. This is also a straight line, positive direction. Right? So look at the time ruler and then choose the answer. Right? Remember this negative sign there. So if it positive becomes negative. That's the one. That's the one. Right? This is longer passing through T1. Straight line, negative, because this negative becomes positive. So answer is A. Can.
Can.
Okay. This one, a solenoid of length 15 cm with 2,500 turns is placed coaxially. Right, they draw for you the diagram, so nothing to worry about coaxially. Inside the solenoid, solenoid is a coil of cross-sectional area 4.5 cm square, has 50 turns. What's the mutual inductance of the arrangement? So this one you require to memorize the formula for mutual inductance. Yeah, that's the formula. L is the length. Okay, put in your value. Okay, that's your mu naught. Area 4.2 times 10 to the power minus 4 convert to meter square. NP 2005, NS 50, and S50. Length is 50, change it to meter. Calculate out. Okay, donkey. Okay, let's do the last one, number 11, I think. Okay or not? Just straight memorizing a formula and then calculate out. Yeah, okay, let's go to number 11. Okay, page 221. A surge coil is worn over the middle section of a long solenoid as shown in diagram. The mutual inductance between the surge coil and the solenoid is 3.60 millihenry. What is the value of EMF induced in the surge coil when the current in the solenoid drops from 1.8 ampere to 0 in a time of 0.04 second? This is basically trying to get you to use remember the formula and use the formula, that's all. Yep, what formula to use? Can you remember? And tell me the formula.
VP over VS and then equals to NP over NS.
Oh, this is EMF. So EMF equals to E. This is a formula. E equals to minus M di dt. That's the change in current against time. That's your M. You cannot use the previous formula that we used because you want to find the back EMF. Put in your value. Right? M, change it to SI unit. And I, this one goes to 0. Change is 1.8. The time is that. Put it in there. So answer is B. Okay, we'll stop here. Any question to ask? Our time is up.
No, teacher.
Okay, if not, we'll see you on Wednesday, 3 to 4.
Okay, you too, sir. Thank you.
Bye-bye.
Bye-bye.